Well, it's my great honor today to introduce our speaker, and it's also my great honor to introduce this as one of our key talks in the 75th anniversary celebration of NASA Ames and the Director's Colloquium Series. Our speaker today is Dr. Ellen Stofan. She was appointed the NASA Chief Scientist on August 25th last year. Almost a year. Time goes quick when you're having fun, right? She serves as the principal advisor to our administrator, Charlie Bolden, on the agency's science programs and science-related strategic planning and investments. She's also a member of the agency executive council, so she speaks for us cool science people. So, you know, you give her a good welcome. She is an associate member of the Cassini mission to Saturn radar team and co-investigator in the Mars Express mission's Marsis sounder. She was also the principal investigator on the Titan Mars Explorer, a proposed mission to send a floating lander to a sea on Titan. That's really cool. You know, and I'm an Air Force guy, but you know, some of the Navy people said, well, they're not talking about flying an airplane in the atmosphere. I said, well, we did, but they didn't get picked. But sailing a boat, so we have a Titanian Navy, right? Ellen holds a master and doctorate degree in geological sciences from Brown University in Providence, Rhode Island, and a bachelor's degree from the College of William and Mary in Williamsburg, Virginia. Her talk today is entitled NASA Science, Looking Outward, Inward, and Homeward. Please join me in welcoming Dr. Ellen Stofan.
Good afternoon. I'm really excited to be here, and I'm excited to talk to all of you, but I understand that a lot of you are summer interns here this summer, and so I was wondering if the interns could raise their hands so I know who you are. Wow, awesome. Oh, Pete. Excellent. So I'm hoping that many of you come back to NASA at some point and join this agency because we're doing amazing things. And I hope to give you a little sort of a broad-based look at a lot of the things we do, just focusing on a couple different areas that I'm particularly working on at the moment or thinking about. And I like to talk about when you think of NASA science, you know, often out in the general public, we were talking about this earlier, there's confusion that NASA actually still exists. But moving beyond that, some people are mostly familiar with our looking outward, you know, our studies of the planets, our studies of the universe, all the great science that we do that often makes it onto the front pages of the newspaper. What they're a little less familiar with, and which there's certainly a lot of expertise here at Ames, is the looking inward that we do, understanding the effects of microgravity on living systems that we are really focused on the International Space Station. And then there's the looking homeward, and I'm going to spend a little bit of time talking about that this afternoon. We have 18 satellites in orbit around the Earth, doing Earth science every day, making critical measurements to help us understand our own planet. And this, to me, sort of summarizes all of the science that we do at NASA, from trying to understand the behavior of our own star, the sun, to our looking back into the earliest moments of the universe, trying to understand the nature of star formation, universe formation, galaxy formation, to the research that we're doing up on the International Space Station to help us prepare to send humans beyond low Earth orbit. From the investigations that we do here in our own solar system, we obviously have spacecraft right now pretty much spanning the solar system, from the Messenger mission at Mercury to the New Horizons spacecraft, which now, a few days short of 1 year from now, New Horizons will have its closest encounter with Pluto, which is going to be incredibly exciting. To get a close look at Pluto, and yes, I know Pluto is not technically a planet. It was when we launched it, that's right. Things change. But nevertheless, and of course, as this image indicates, the Juno mission, which is going to be studying Jupiter soon. So really, spacecraft all across the solar system. Almost every day, you can go onto our NASA websites and find some cool solar system science that's been returned. And finally, again, the work that we do observing our own planet, just about in every wavelength of the electromagnetic spectrum, from regions like our fragile coastlines to observations of the ocean, the Earth's atmosphere. But when you look at NASA, this is pretty much how we're organized in these different divisions. And as chief scientist, I have the fun job of being able to look across all of this science that we do. And one of the things I like to do is try to communicate the connections, because there are huge connections between all of these different areas of science we pursue. We might be organized into these stovepipes, but we actually, a lot of us don't operate that way. And if you think about the fundamental questions that drive what we do, and you can find these questions in all of our driving documents, the decadal surveys that the National Research Council helps the community put together. What are sort of the top questions in science? And those fundamental questions are how NASA develops its science policy, how we decide what to do next. We really look out to the community through those decadal surveys. Then we develop our own strategic plans, and really in those documents, you'll find basically these three questions, which are getting at how does everything form, what's the origin of stars, of planets, of the universe, and then how do they change over time. And so today I wanted to start out talking about that bottom question. How does our universe work? Because as a planet, we really want to know, how does our local solar system environment evolve over time? How has that affected the Earth both in the past and moving into the future? And certainly one of the fundamental issues with that is what's going on our sun. We get these huge eruptions in coronal mass ejections, solar flares of particles that come streaming towards the Earth. As those particles go by, for example, Venus does not have a magnetic field, so that solar wind, those stripping of particles actually strip away the top layers of the atmosphere of Venus, contributing to the fact that Venus now has this incredibly inhospitable climate. But when they reach the Earth, those were protected by our magnetic field. And so those wonderful magnetic field lines send all those particles around the Earth, protecting us from solar particles, protecting us from cosmic rays here on the surface of the Earth. But obviously, if we want to send astronauts out beyond our little pale blue dot into deep space, we have to learn how to protect them from that harsh solar environment. And again, that's some of the research that we're doing right here at Ames, but also up on the International Space Station every day. So if you really think of the Earth as being this fairly fragile little pale blue dot in space, that can be hugely affected by things like solar storms, you can then turn to what's going on our planet right now. And these are the deviations from average surface temperature starting in the 1890s and going all the way to the present. So from natural effects like a solar storm to man-made effects or climate change. And as you see, especially moving into the 1990s, into the early 2000s, when you see that temperature just going up and up and up, with particularly strong effects in sub-Saharan Africa, where you have populations that are really the least able to adapt to any kind of climate change, to huge changes going on in the Arctic. And again, as you see this cycle back around, you'll see going from about the late 90s to the present, the temperature just going up and up and up in the Arctic region. Huge impact on the populations that live there, and really a sort of a bellwether for what is going to happen to the rest of the planet. And obviously this is having huge effects. That concentration of higher average surface temperatures up in the Arctic is having a practical effect. It's melting the polar ice caps over time, so that every summer, more or less, we have less and less surface area in the Arctic Ocean covered by sea ice. Sea ice that remains tends to be thinner. It tends to often be darker, so that polar Arctic region absorbs more and more heat. That is then given off. It's dumping energy into our climate and weather system. And what's the effect of that? To be honest with you, we don't know. Just this past year, through the National Academy or the National Research Council, there was a big meeting of scientists getting together and debating, what is the effect of this increased heat pulse into the Arctic region? Is it causing some of the weird weather we had on the East Coast, for example, this past winter? We don't know yet. It's too soon. We don't have enough data. But the fact that the Arctic is changing so much, so rapidly, to the point, again, by the 2030s, we think there'll be very little ice cover in the summer in the Arctic. It's clearly having long-term implications, again, not just on the people who live in the Arctic, but on the rest of us. And so it's frustrating for many of us when you say, well, when climate change occurs in the future, and you say, okay, for the people who are living in the Arctic, it's something we observe every day. Now, if you say, okay, how can NASA actually play a role in this? And clearly, again, we have those 18 satellites, not to mention the aircraft program that we do. We have those 18 satellites, and all different instruments, every phase of the electromagnetic spectrum, where we're observing at different times of the day, at different intervals, atmospheric chemistry, cloud cover, surface land change, surface winds, upper atmospheric winds, a whole range of measurements to get at each of these different aspects. We have this incredibly complex planet. I always tell people that's why I'd rather study Venus or Titan, because you don't have all this pesky vegetation and people and stuff around. So they're much simpler. So if you're trying to understand a planet as complex as the Earth, you need an awful lot of data to do that. And obviously you're also doing great things here at Ames through the next program on trying to make that data more easily available and usable to the broad community. And so this year is a year that we're in particular really excited about. For the first time in over a decade, we have 5 Mission to Planet Earth missions being launched this year. The good news is 2 of them have already launched, so we have 3 more to wait for. GPM, the Global Precipitation Measurement Core, was launched in February. OCO2 was just launched at the beginning of this month, and both satellites are doing really well. What I love about the missions, especially that we're launching this year, is you can really illustrate how NASA's trying to attack these fundamental problems in such a comprehensive way. Take GPM and SMAP. And on that previous slide, you saw the water cycle. Well, you can think of water as sort of being a proxy for energy, and that's obviously really critical to the workings of the climate system. With GPM, we're measuring global precipitation around the globe every 3 hours, and we're not just measuring how much did it rain, we're measuring what was the size of the raindrops, was there ice mixed in, a favorite of ours on the East Coast, mixed precipitation, and the sizes of those ice droplets, was it snowing, sleeting, and exactly what kind of precipitation is going on. And again, that's important for one thing, because again, water can be thought of as a proxy for energy in the climate cycle, but also because, go back to the fact that over 70% of the Earth's surface is covered by water. All right, nobody's out there with rain gauges measuring how much it rains or knowing what type of precipitation is falling. So space-based measurements is the only way we can get a comprehensive look at that input into the water cycle. Now, SMAP is taking a different look at it. SMAP is measuring soil moisture. So, okay, again, think of the water cycle, precipitation, evaporation, there's something else in there. I'm not good at that song my kids can sing. SMAP is going to be measuring land surface soil moisture. Again, critical to understanding the water cycle, but also critical on a fundamental scale to farmers who want to know how much water their soil is retaining, where are the wet areas, where's it dry, what are the trends, how can we input that data into models. Now, a satellite that we've already launched that's not on this, GRACE, is taking another part of that water cycle issue. GRACE measures changes in the Earth's surface, gets at gravity, but we can also actually use it to look at aquifers. When aquifers have been going, in general, down these days, for example, in India, we've seen it here in California, we've actually been able to measure very precisely when the Earth's surface goes down because we've been draining aquifers, in a lot of cases, irreversibly, they're not filling back up again. And so we can actually go into the third dimension, down into the surface of the Earth, and understand more about the water balance on the planet. So with 3 NASA satellites, we're actually attacking all different pieces of this water cycle. So not just a piece of information here or there, but a whole series of pieces of information that we can knit together to better understand some of these very fundamental cycles on our extremely complex planet. And the other thing I will say that's exciting about this year is that 2 of these instruments, RapidScat and CAT, the Cloud Aerosol Transport System, are both going to be mounted on the International Space Station. So being able to utilize this amazing platform that we have in space to be doing Earth science observations in a different orbit than a lot of the polar orbits that we put satellites into. It's very complementary to a lot of the other data sets that we're collecting, so we're really excited about that also. Now, if we're trying to understand this complex planet, again, it really helps to put it into context. And for a lot of you summer interns, a lot of the times when I'm telling people, for a long time, people will say, why do you study those other planets anyway? And I try to use the analogy of just think if you were a doctor and you only had one patient. You might really start to understand that patient, like when they might get sick, when they might get better, how resilient they are to disease. But you'd never be able to understand the nature of disease unless you had lots and lots of patients. And I would argue as a geologist, we have that same issue if we only have the Earth to study. I primarily study volcanoes on planetary surfaces. And so if I can have multiple bodies to study that have slightly different temperature and pressure, slightly different rock compositions, maybe sometimes the rocks are more wet, more dry, different atmospheric pressure, different atmospheric temperature, different gravity, I can start knitting all those different physical situations together and start to better understand how a physical process, the eruption of a volcano, how that operates. So by having not just the Earth, but Venus, Mars, the icy satellites in the solar system, I can do comparative planetology and I can start understanding how planetary processes better work. And obviously one of the things we really like to do in our progression of how we study planets is go from orbiters that collect remote data. Well, we usually start with flybys when we can't get into orbit. And then we orbit and collect global comprehensive data sets. And once we have a good idea of the global nature of a body, we like to get down on the surface, whether it's getting down on the surface of an asteroid, the moon, Venus, as the Soviets did back in the 1980s, Mars, which I'll talk a lot about in a minute, one of my favorite places in the solar system, Titan, with those little white round pebbles. And then, of course, we have these bodies to actually compare back to the Earth. So when we have that in situ, that surface data, we can start really looking at geologic processes like how do lava flows form. We can look at those very smooth, platey lava flows on Venus and start to better understand how they compare to volcanic eruptions here on Earth. We can look at those little rounded pebbles on the surface of Titan and know that to get a little rounded rock like that, it has to be tumbled by a stream, tumbled in a river. And indeed, that is what happened to it. But of course, those rivers and streams have liquid methane and ethane flowing in them, not water, because on Titan, it's 94 degrees Kelvin on the surface. Really, 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 really cold. So water is not stable as a liquid, but liquid methane is. But all of a sudden, we have these same processes that occur here on the Earth, rivers, streams, lakes, seas, and all the processes that come with that, waves, currents, tides. But now it's on a body with a different working fluid, different gravity, whole different world, something to compare the Earth to better understand, for example, marine processes. Extremely exciting. So it's something we'd like to ultimately someday investigate a little more closely. Now that top question on that slide, I've been mostly talking about how the solar system works. And the top question on that list was, are we alone? And if you go out to the general public and start talking to them about the science that we do at NASA, that's probably the question that I get asked most frequently. Most frequently it's, do you think there's life on Europa or Mars? And then it's, would NASA tell people if we found it? Yes, of course we would tell people if we found it. But this question of are we alone, I think is one that resonates with everybody because it's such a fundamental question that you have, that humans have had forever when you look up into the night sky and say, are we the only things out there? Well, obviously, approaching that from a scientific point of view, you say, well, what were the ingredients here on the Earth that led to the formation of life? And those ingredients that we've come up with are a source of energy and nutrients. That's pretty easy in our solar system with volcanoes, lightning, lots of sources of energy, sources of nutrients. Advanced carbon compounds, again, not very hard. occur in lots of places. I was hearing today, out in the interstellar medium, comets, asteroids, everywhere we go, we find carbon compounds. So that's not the tough part. The tough part turns out to be liquid water, which we think is critical for the formation of life. And liquid water, water's obviously only stable as a liquid in a fairly limited temperature bound. So where could we go in our solar system to find those conditions? I would argue there's also a fourth condition to those three, and that's stability of environment. That if the conditions are changing all the time, it's going to be really hard to allow the chemistry to go forward to get very much life to occur. So maybe it's going to be really hard to find. So the longer those conditions where liquid water is stable, for example, persists, a stable radiation environment, a more or less stable temperature and pressure environment, the more likely you are to get life. Well, in the center of that slide is obviously one of the chief areas that we're trying to study. Mars, and that's Mount Sharp, which the Curiosity rover is in the process of climbing, getting back really exciting data from its multiple instruments, trying to get at this question of were there habitable environments on the surface of Mars, and if so, how long did they persist? And the news that's come back from Curiosity has been exciting. Okay, we've known for a long time there was water on Mars. Some of the results from Spirit and Opportunity said, well, some of these environments, aqueous environments, maybe weren't all that welcoming to life, but the environments that have been identified at Gale Crater seem to be, again, long-lasting and much more conducive potentially to the formation of life. So we've been really excited by the results coming back from that. Not to mention that one of the instruments on Curiosity, the mass spectrometer, has actually been able to get some exposure age dating, which is the first age dating we've been able to do on a planetary surface. Age dating is really important to geologists because it allows you to put absolute dates on things rather than saying, okay, these rocks are older than these rocks, but I don't really know when they formed or how long they took to form. Age dating allows you to put a specific date on the rocks and actually start to understand how long have these rocks, for example, been exposed to cosmic radiation. When did they form? A critical tool that we've never had on a planetary surface until Curiosity. So really exciting. But the other places that we'd go in our solar system is up there in the upper right, Europa. Europa is a moon of Jupiter. It has an icy crust. And under that icy crust, we know there's a liquid water ocean. And at the base of that ocean, there's a largely silicate core. Now, Europa is obviously, as I said, in orbit around Jupiter. Jupiter is extremely massive, so it's always pulling on Europa. It is always tugging also huge tides on Io, one of Jupiter's other moons, and Io is covered with volcanoes. Okay, Europa is a little further out from Jupiter, but still close enough that it has huge tidal effects, up to 30 meters, from that pull of Jupiter. Okay, so that silicate core inside of Europa is constantly moving around. That moving around creates frictional heat, enough to melt, enough to cause volcanism. Okay, so think of that icy crust, a big thick water ocean, and then at the bottom of that liquid ocean, volcanoes. All kinds of volcanic vents. Volcanic vents produce heat, they produce lots of nutrients, all kinds of minerals, a great environment potentially for the formation of life. And so one of our primary targets, in fact, just last week, we released an announcement of opportunity for people to start thinking about instruments for the next mission to Europa, which we hope will take place in the 2020s. On the bottom, you see Enceladus, which is another moon of Saturn, like Titan. Enceladus also has a liquid ocean, but in this case, we think it's a lot smaller, more like a liquid sea underneath its icy crust. So again, no real atmosphere, icy crust, subsurface, small in this case, probably sea. Enceladus is also being pulled on by Saturn, and that causes cracks in the surface of Enceladus. And it turns out you have geyser-like eruptions coming from that subsurface ocean, spewing material out. Luckily, with the Cassini spacecraft, we were actually able to fly through those plumes, so we know they're partially water and water ice. But we also know there's all kinds of complex organic compounds coming out from the interior. Now, we don't know exactly what they are because the mass spectrometer on Cassini really wasn't designed to be able to specify exactly what they are, but we know they're complex carbon compounds. So Enceladus is another target potentially to go to in the future to really understand how many places in our own solar system could be conducive to life. In the upper left, you see Titan. Again, I talk a lot about Titan, which Natalie Cabral will appreciate. But Natalie and I are particularly interested in Titan because of the fact that it has these seas on its surface. Very long lasting. We think they actually persist for likely tens of thousands of years. The seas, again, not water, liquid ethane and methane. All kinds of complicated organic compounds, some like plastics, are forming in the atmosphere of Titan. They form solid particles called tholins. Those tholins rain down into the seas and persist in those seas for probably, again, very long periods of time. Okay, there's no liquid water, and it's cold, again, extremely cold. So could you have enough energy that would lead towards anything that looked like life? Could you only get some of the way there, but not all of the way there? We have no idea. But if you really want to push on the limits to life, after we explore the places where we think are more likely because there's liquid water, Titan would certainly be high on the list. The other reason we're particularly excited about Europa right now is this is a mosaic of near the southern polar region. And from some of those cracks that you see here near the South Pole, Hubble took some observations. Well, okay, a scientist made Hubble take some observations last year of that region. And what they saw was a hydrogen and oxygen cloud, basically, around that region of Europa, seemingly indicating what actually a bunch of scientists had been predicting for some time. When they saw those plumes on Enceladus, they thought, you know, Europa's got all these cracks. Europa's in this similar situation being tugged on, just like Enceladus is. Maybe we have similar plumes coming out of the pole of Europa. The planet was actually also at about the right point in its orbit around Jupiter, where you'd expect it to be really being yanked on, so that would be maybe the maximum time of crack opening, so when you would expect a plume to be forming. Now they've looked again and they haven't seen the plumes, so there's a whole bunch of observations planned to go back and look again and say, can we see these plumes, can we understand? Now obviously that would hugely affect what you might do next at Europa. Because for a long time, we've certainly been wondering, for example, there's this kind of orangey brown stuff on the surface. We don't know what its composition is. That's one thing an orbiter or a mission that was in Jupiter orbit going by Europa would certainly get at what's the chemistry of that. But because of that harsh radiation environment, extremely harsh radiation environment because of Jupiter being right there, we don't really think anything could live on the surface of Europa. So anything that's living would likely be subsurface. Okay, you think, okay, from an observational point of view, how am I ever going to get at the composition of that subsurface ocean if all I can do is look at the top of the icy crust? Well, we're certainly interested in what that material is on the outside, but the fact that Europa might actually be spitting at us samples of its interior ocean is extremely exciting from an exploration point of view, because it means we can access that material and analyze it without having to do all the cool things that you read about that people think about, like melting down through 10 kilometers of ice and putting submarines into the oceans on Europa. Cool things to think about, but if I want this question answered in my lifetime, my bet is we're going to have to really analyze the material coming out in those plumes. So really exciting work to do at Europa. But in the meantime, we're doing all this exciting work at Mars, and this is just 5 of the 8 places we've landed on the surface of Mars. And when we think, you hear NASA more and more talking about humans to Mars, that it's really the direction we want to go. It's the ultimate destination for getting humans down on the surface. And John Grunsfeld, the Associate Administrator for Science, likes to remind everybody, we're already deep in the process of exploring Mars. This is not something new that's NASA doing. The humans would be following in the footsteps of the extensive work that we've been doing robotically, laying the case to me scientifically for some of the reasons that it's so important to actually get scientists down on the surface of Mars. Lots of different environments that we've explored, both in situ and remotely. And the more research we do, the more we're able to refine where are the best places to actually go and explore, to try to really push at this question of did life evolve on the surface. And so we think of the eventuality, in my mind, again, being somebody who values field geology hugely. If we're ever really going to resolve this question, I argue it's going to take astrobiologists on the surface of Mars, probably with a laboratory right there, working in a lab on Mars to actually demonstrate, yes, life evolved, because I think it's going to be pretty hard to find, and I think there'll be a huge debate in the scientific community over, is this life, is it not life, is it the building blocks of life? So again, as a field geologist, I'm anxious to, as soon as we can, get those scientists onto the surface of Mars, doing what we do best, exploring in situ. An exciting future to think about. And hopefully, again, as early as the 2030s, getting us down onto the surface. Now you can say, okay, can we do this? And some of you know, my father worked for NASA, and I found an interview with him that was done in the 1980s. And he was saying he was really excited because in the next 20 years we were going to put people on Mars. And it's like, this is depressing. But I'm confident that if we put our will to it, we can do it. And what I like is we have this formulated road to Mars, and we're well on the way to attacking bits of this problem. To start at Mars, again, we have, I don't want to call it a flotilla, that sounds, well, first of all, nautical, but anyway, we have these wonderful spacecraft assets in orbit, on the ground, identifying where the best science is, really getting at a variety of scientific questions, but again, centering around this question of did life evolve on Mars, but also doing a lot of the characterization of the Martian environment that we need to do. And don't get me wrong, we need to do a lot more, things like what's the exact nature of the dust on Mars that could be hazardous to humans trying to work on the surface, but trying to fill what we call the strategic knowledge gaps to get ready to safely send humans to work on Mars and return safely back to the planet. In the meantime, with humans, we're doing the work that we need to do in what we call the Earth Reliant. Just up on the International Space Station, where we can easily and safely return home to Earth, we're doing this broad range of research to understand the effects of microgravity on the human body. And most of you know, a lot of huge negative effects, muscle wasting, bone density loss, raise of intracranial pressure, so you get pressure on your eyes, it affects your optic nerve, effects on your immune system, all of these things that we actually have a really detailed list of here are the risks to humans for a trip to Mars that we need to do research, both a mixture of fundamental research and mitigation efforts, to try to make sure that we can safely send humans to Mars in the next 20 years and return them home again. So a huge amount of work being done in this Earth-reliant area, not to mention technology development. Most of you are aware, a couple weeks ago we tested a supersonic parachute, and we want to do more with technology testing, both from the ISS and here on the ground, just try to start buying down some of the big risks like entry, descent, and landing that we have to overcome to be able to send humans safely to Mars. And then ultimately, we want to go out to what Bill Gerstenmaier calls the proving ground, out in the vicinity of the moon, where we can start going that next step in a more hazardous radiation environment, in a more non-Earth reliant but still able to get home in a few days environment to, again, push these technologies, push developing habitats, push extravehicular activity, ECLIS, all these different systems that we need to use to get humans to Mars. But the work that we're doing on the International Space Station, I think, is particularly critical. We just got extended through 2024, a critical time period for scientists. If you want scientists or, for example, commercial entities to be able to say, how can I really use this as a platform? Having that extension out to 2024 give somebody the reliability to say, I can do a scientific experiment, then I can follow it up, then I can follow it up again. So having that stability of the station out to 24, I think, is really critical. We are, with commercial cargo, really coming online. We're able to start more and more regularly, having regular up and down, well, up mass mostly, hopefully soon better down mass coming from the station. Again, making it a reliable environment for scientists to do research. So really excited about a lot of work that we're doing there. And today I've been talking about some of the work that we're doing up on the ISS primarily for getting ready to go to Mars. But obviously there's a huge range of research going on in other areas, from the cold atom lab, where we're going to be studying atoms that are cooled down to almost absolute zero and studying that behavior. That's going to go up in about 2018. To the work we do in combustion, identifying a new phase of combustion that we're doing work with. All the work in materials science, materials production that in microgravity is so different, crystal growth. Huge range of research that's going on the International Space Station every day. Really exciting. Now, some of you have heard me talk before. You know how much I love this image that was taken last summer of the by the Cassini spacecraft, 1 billion kilometers away from Earth, looking back at the Earth and observing us as this little pale blue dot in space. Redoing the original Carl Sagan image that was done with the Voyager data. And I think, again, if you go back to the beginning of my talk, talking about how we're this pale blue dot in space, subject to the behavior of our star, subject to our own misuse of our planet. Here you can step back and say, what a technological feat that we have gone over 1 billion kilometers from our planet and can look back and study it. And so if you look at this now close up from that same image of the Earth-Moon system, it brings up another question. Finding an Earth-like world around another star. Here we're able to look at our own planet as though we were remotely imaging a planet around another star. Just last week at NASA headquarters, we had a colloquium called The Search for Life in the Universe. Sarah Seeger was there, and it was really amazing to me, which is something many of you in this audience have probably thought of, but it really blew me away. She said, every time you look up in the night sky and you see all these stars, around every one of those stars is probably a planet. From the data we've found, from Bill Ruecke's hard work with Kepler, what we've been able to know is that when you look up in that night sky and you see a star, that star probably has a planet. When we look into the deepest, darkest part of the sky, this is what we find when we look at it with Hubble. Tons and tons and tons and tons of galaxies. Very, very young galaxies, very, very deep in the universe. Again, those galaxies full of stars, so full of planets. And I think one of the most amazing things to me, the most exciting things that's come out of Kepler is not just single planet systems, but multi-planet systems. Solar systems to start comparing to our own solar system. And just like with the planets, when you go and you say, okay, how does a volcano work on Venus or Mars as opposed to how it works on Earth? And you start learning all kinds of things about volcanism that you didn't expect. That's happened in spades so far in our study of extrasolar planets. It has caused the model that I learned 4,000 years ago, as my children would say, in graduate school to be basically thrown out. Our model of how we thought our solar system formed, how the planets condensed from this tidy little cloud where you got those rocky planets close to a sun and gas giants further out. And that was the model I was taught in graduate school. Nah, gone. Because we've found that gas giants can form very close to their parent star and migrate outward. Planets can form in ways that we didn't expect. And that to me is the true magic of something like Kepler. It's the true magic of what we're going to be able to do with JWST. We're going to find those actually Donald Rumsfeld's unknown unknowns. We're going to find the things that we actually didn't expect, because that's where you really push science forward. We have whole new models now of how we think solar systems form. And I argue we're probably even now only seeing one small part of the problem. As we develop better and better telescopes, look with higher resolution into other solar systems, we're going to learn so much more and refine those models. And I'm really excited for 2018 when we launch the James Webb Space Telescope. And we have the ability not just to detect, okay, here's a new planet, here's its likely mass, here's its likely orbit around a star, but we're actually going to be able to start looking at the atmospheres of those planets and saying, what are those atmospheres actually made of? And into the future, as we're able to develop larger and larger aperture telescopes, to actually be able to say, okay, how do those atmospheres change over time? And can we image one of these planets around another star to try to find that habitable world around another star? Getting back to that question, not only are we alone in our own solar system, but are we alone in our galaxy, in our universe? Really critical questions. And again, highlights the importance to me of really nailing down this question in our own solar system. We'd like to use our own solar system to get ready, to me, as we, in the next 20 years, really turn the study of extrasolar planets into what is really a new science, into a major field of science. Incredibly exciting time to be in this field. Everything is changing. You know, at NASA we innovate, doing things like building these giant mirrors that are going onto the James Webb Space Telescope. And for you guys in the audience, there's a video online that shows how James Webb is it's way too big to fit with those mirrors all spread out. And so when it gets launched, everything is all folded up to fit inside the shroud. So after it launches, the whole thing has to deploy. As somebody said, I think they said it was their like 8 days of terror as opposed to that 7 minutes of terror landing on the surface of Mars. Anyway, amazing technological feat, really exciting. Stay tuned for 2018 and James Webb, and watch that video on the web. You know, in NASA, we're able to explore. We have explorers right here at Ames, again, my friend Nat, who gets out in the field. At NASA, we get out in the field, we do experiments, we study, we're up in the Arctic, we're down in Chile in the mountains, we're all over this planet trying to better understand how our own planet is changing and the implications of that for other worlds like Mars, like Titan, like Venus. We make discoveries every day. The scientists here at Ames, the scientists that we have across the agency are using information, whether it's coming from a spacecraft or up on the International Space Station, to make new discoveries, really push science back. And hopefully in doing all of these things, in innovating, in creating things like James Webb, in exploring, in discovering, we're actually inspiring the next generation of space explorers. And I hope that many of you who are here as interns this summer can join us in the future and help us on that road to Mars. Thank you. And I actually prefer answering questions to talking, so thank you.
Thank you. So we have time for a few questions. As usual, please raise your hand if you have a question, wait for the microphone, and stand up when you ask your question.
There's about 1 million near-Earth objects big enough to destroy a city, and we don't know where 99% of them are, and one hit us last year. You didn't mention it. Could you talk a little bit about what NASA's doing to understand and mitigate that threat?
That's a great question. And obviously, you know, again, back when I was in school and we learned about the Tunguska event, where this meteor came in over Siberia and exploded and knocked down, hundreds and hundreds of acres of pine trees in Siberia. And I thought, wow, this is never going to happen in my lifetime. And then poor Siberia, with Chelyabinsk, gets hit again last year, and luckily, obviously, no loss of life, but some amount of damage. Asteroids are a hazard. Comets and asteroids both are a hazard to planets. It's what, that's why the moon is such a great place to study, because it gives us that cratering history that erosion has wiped away from the Earth. And NASA right now, our major effort is in trying to characterize that population of Earth-crossing objects above about 2 kilometers in size. So we reactivated the WISE spacecraft, now called NEO-WISE. There's a huge Earth-based program of observation, and it's really to try to characterize that population of Earth-crossers down to a smaller and smaller size. Obviously, when you are looking for things that small, and in general, you're trying to find them when they're far away, so they're very faint. So it's a challenge, and it's going to take us a little longer to build up the full database than we had hoped. But we're continuing to do it because there's no question that things have hit us before, and they will hit us again.
So what would be some of the ethical and scientific consequences if we found life on another planet, like, for example, for colonization?
Well, you know, one of the first things that I think it's important to step back and remember is one of the chief things we do at NASA right now is to try to make sure that when we go out and look for life on another planet, that we don't rediscover life that we brought along with us. And so planetary protection is a huge issue. So one of the things that we do really rigorously is when we send spacecraft, for example, anything that goes to Mars has to go through really rigorous processes to make sure it's biologically as clean as we can make it. The same goes, for example, with the Cassini spacecraft has to be kept away from Enceladus, and anything that goes to the Jupiter system has to be kept away from actually like crashing into Europa. So one of the first things that we do is try to make sure that any life we found, we didn't bring it with us. So we try to make it clear when we eventually do find it. You know, I think on one level, obviously one of the things you're really going to want to do is to really understand how similar or dissimilar is any life you find to life here on Earth. You know, does it have DNA and RNA? What are the characteristics of it? How different is it? Does it use sugars and proteins in the same way? So huge, just fundamental biological questions. We have one example that we have studied pretty darn well, and we don't have any other examples. And so the scientific advances that we will make when we find life on another world, I think is exciting. And frankly, I do think it's going to happen in our lifetime because I think both Europa and Mars are great candidates. So I'm pretty excited about it. You know, ethically and philosophically, you know, you can say it's just going to blow everybody's mind. You know, that's not a great answer, but I think it's true.
I think the discussion of climate change is extremely important. And it seems to me that NASA should be really very active, not only providing experiments to try to understand the space station and so on, but an educational program that brings the concerns and interests in science to the public, and particularly young. Is there an educational program now that the educational program has been, to some extent, divorced from NASA, that allows NASA to continue to help young people learn about climate change?
The science, Bill, I think you're absolutely right. It's such a, you know, putting everything aside, you know, climate change is the challenge. You know, it's got to be addressed, and that education bit is a good part of it. Though I will say most audiences you go out to, if they're under about 14, they're pretty much in line. If they're above 14, that's where it gets more dodgy. But I think there is still a lot of education work that's going on through the Science Mission Directorate and through the Earth Science, and climate change is a critical part of all of that. And I've taken part in two recent events, the Climate Data Initiative that was announced at the White House, and then when the National Climate Assessment came out. NASA's been playing a huge role in that, and that's not so much aimed at education as it's aimed in how can we take all of this data that we collect at NASA that scientists are using to analyze climate change in ways that are really important. I don't want to make light of that. But how can we take that data and actually make it more accessible to, say, a city manager in coastal North Carolina? How can they understand, you know, based on current models, what are the chances of coastal inundation, coastal flooding in this area over the next 10 years? How can we make these predictions and these data that we increasingly now have on a regional level as came out in the National Climate Assessment? How can we make that data available to decision makers, maybe not on the national level where there's so much noise, but down on a local level where, for example, in Norfolk, Virginia, you know, it's flooding already. There's subsidence combined with sea level rise, and there's a huge amount of money being spent to try to fix it, and it's not going to get fixed. And so I think trying to make sure our data sets are readily available to those decision makers out there is as critical as the outreach bit that we do, and it's incredibly important. I will say it's a source of frustration to many people in the agency that if we go out and talk about climate change in Mars, the press quotes us on Mars and not so much on climate change. And I do think there's a lot of people in the agency trying to talk about climate change, but the message doesn't always make it to the general public. So I would urge all of you who go out, I show that temperature video, which is available through that's the Goddard Institute of Space Studies, but you just Google climate change or temperature change. Every time I show that video to the general public, in general, I have people gasp. They just don't. There's so many people in the general public who just don't understand that when we talk about the fact that the planet has warmed over the last 20 years, they think we're making it up. And when you show them that, they say, wow, that's data. I get it. And I can't tell, I've had floods of people come up to me. I've talked to like a local women's group, and people will come up to me and say, wow, that's kind of scary. And you're like, yeah, it is kind of scary.
You talked about dating rocks on Mars.
That sounds kind of odd, but yeah.
Well, I was wondering how you go about doing that, because if you do it with isotopes, I know on Earth you have to use some pretty complex tables that have been developed over the years determining what amounts of each isotope were present. How do you go about doing something like that on Mars?
It wasn't my research, so I can't exactly quote it to you. I'm pretty sure they use, somebody can shout out and correct me if I'm wrong, I'm pretty sure they use potassium argon, though they might have used rubidium strontium for one of the others. They did a couple different dates. But they were able to get, again, you have to make assumptions. So it's not like there aren't error bars, and the error bars are because of what you just said. You have to make assumptions about the original content of each of the radioactive minerals to be able to do it. But given those assumptions, which make your error bars go up as opposed to the much smaller error bars we have here on Earth, you still are able to get an age date. And again, we're able to kind of fit it in with everything else we know about Mars that actually makes sense geologically. Bigger error bars than we would like, but still an actual age date. And again, hugely powerful. Now be able to think of sending those lots of places on Mars, again, being able to get rough age dates. On Venus, which we would love to know, there's a huge debate on the surface of Venus over when much of the surface formed, relative age of surface units, and Venus is a whole nother struggle because the temperatures are so high, the systematics might reset, complex geochemistry stuff. But still, some of the issues that you talk about, still getting pretty crummy ages is a lot better than what we have now. So really exciting to move the technique forward off the planet.
Hi, you spoke a lot about some exciting planetary missions with a lot farther time outlooks. How do you plan for funding these kinds of long-term, really exciting, really hard-to-do missions across so many administrations and timeframes? And then is there anything as engineers that we can do to help enable these kinds of missions under tighter budget constraints?
Well, obviously, to some extent, we're a 30-year agency that lives in a 2-year town. And you know, that has always been the way it is. And so what it takes is a consistent story that's broadly acceptable. If you think of how did we get to the moon, which took an enormous amount of resources, we had a consistent story that was broadly accepted by the government as the right thing to do. And so that's a hard thing to do, right? To get broadly acceptable. How well does that play in Washington, right? I mean, so trying to operate. The good thing for NASA is we actually have had for a long time huge bipartisan support. I mean, I can't tell you, when I go up on Capitol Hill and congressmen find out I work for NASA, the first thing they normally say to me is, I love NASA. I love you guys. And I think even when people say, well, the federal government is spending too much money, I think people say, well, okay, we need to make sure NASA has not unlimited resources, but they understand the benefit. I'm not having to sit there and explain, you know, it's an investment in the economy, huge scientific return, public inspiration. They get it. On the other hand, the federal government has a limited amount of money, and there's a lot of pressure on that limited amount of money. So I think the more at NASA that we can get out there and tell our story, the more we can convince a very distracted public who's distracted by lots of different inputs, that what we're doing is valuable and cool. And that's obviously on a lot of us who do it on our own time. But the public generally really appreciates it. They love hearing about what we do. So the first thing you can do is get out there and talk. And I know it's on your own time, and that's not always great. But the more you get out there and talk about the cool stuff that we're doing, the better off we're going to be. And then it's on the NASA leadership to make sure that we have a plan like the Road to Mars, where we can say, here's what we're doing, here's why, here's how we're going to do it, and here's how not only is it scientifically important, it's laying out a technological challenge for the nation, for the international community, that's important for long-term investment and skills that we need as a country to move forward.
All right, so please join me in thanking NASA's Chief Scientist, Dr. Ellen Stofan.